that. Get that out of the way. Make sure my microphone is on. Awesome. So, atomic structure and atomic notation is the title. Looking at that diagram, that's a typical diagram of an atom, all right? We now know that the atom doesn't look like that. By the end of today's class, we're going to be doing Bohr diagrams and something called Lewis diagrams. But you've done Bohr diagrams before, and you've got the picture in your mind in the past of the fact that there are these rings around the nucleus that the electrons exist. I mentioned, yeah, Abby's already looking over her shoulder, and she's going, lies. He's going to tell us lies. And I am. And that's going to happen throughout your chemistry career. I remember feeling quite bitter as well when I had a professor tell us, well, you know what they told you in some of those high school classes? Well, they were telling some little white lies. And I was like, what? You mean all of those years of chemistry in high school was a lie? And now that I teach, I realize it's not a lie, but we teach you little baby steps at a time. Because if I were to explain to you the way we really think of the atom, it would become so complicated and scary that you wouldn't want to learn about it anymore. So we teach you little baby steps at a time. So we're going to stay with the rings for now. And even next year, we're going to stick with the rings. And then grade 12, we'll teach you about quantum theory and probability distributions and, oh yeah, it's awesome. Wave functions. It's really cool. So little baby steps for now. But this picture is even kind of before the idea of the rings, right? You'll notice these electrons are just kind of whizzing around in some kind of an orbit here, but the orbits are not necessarily in certain distances and in certain positions, all right? We sometimes call this the Rutherford model because Rutherford discovered the nucleus but didn't really state where the electrons had to exist. It was Niels Bohr who came up with the idea of the fact that there are these energy levels or rings that can contain certain numbers of electrons and therefore give them certain locations in space. But this, for some reason, has kind of stuck around as being the iconic atom. It's like what you would see if you thought of an atom or you saw it on TV or whatever, some kind of a show, you'd have a picture like this representing the atom. But it really isn't a very good representation of the atom. It's not bad. It's got a nucleus and it's got electrons going around it. But we now know they don't just whiz around like that. Okay? All right. So let's bring up some information about the atom, and you can write this stuff down. Now that table at the bottom, you don't have to make a big table with the ruler and all that stuff. If you'd like, you can, right? If you're one whose notes, don't involve rulers, which is the way I was when I was a student, still is now. If I'm making a note, I'm just scribbling things down. You can use the lines on your page. It doesn't really matter. But we've got our three main particles that are found in the atom. And again, this is very much review, right? You've heard of all these particles? Yes? Yeah? Yep. I'm not going to lie, I didn't put this PowerPoint together. I like the most of it, but I do have an issue with one of the pieces of information on this chart. Yep. Yeah, it's really small. Let's change that to 1/2000. Have you already put 0? If you've already put 0, in beside it, just put here, very small. It does have a mass. Its mass is approximately, it's not exactly 1/2000, that would be really cool, but it's approximately 1/2000th of a neutron or a proton. It's actually about 850 something. Actually, I'd lie if I told you it was 50 something, but I know it's 800, and it's in the high 1800, not 800, 1800, in the high 1800s. But that's close enough. So an electron does have mass. That is very important. It is a piece of matter. If it didn't have mass, it would be something else. Would it be light? It could be, but it's not. It's a piece of matter. What we want to state here, though, about the electrons is that it doesn't contribute to the mass of the atom. If an atom loses an electron in a chemical reaction, it doesn't change the mass of the atom. In other words, the change is so small that it doesn't have an effect. I don't know. I guess so.
Thank you.
Yep. It's essentially, so if an atom loses an electron in the process of a chemical reaction, we still say that the atom, the ion that's formed, has the same mass. It would be the same as you weighing yourself, going and getting a haircut, and then weighing yourself again, and noticing that you really haven't changed when you look on the scale, right? Even though your mass has changed slightly, you really wouldn't, go to your driver's license and change your mass just because you had a haircut, because that little bit of hair doesn't weigh very much. Same type of thing. Electrons are very light, all right? So we've got the proton. Its electrical charge is 1. Its symbol is P with a little superscript plus to represent the charge. It's found in the nucleus, and it has a unit of one mass unit. And don't worry about what the unit is. It's not grams. It's not kilograms. It actually does have a value. The symbol is U. It stands for an atomic mass unit, and it's a very, very small mass, but don't worry yourselves about it. Now, the neat thing about the electron, let's jump over to it. Even though the electron is phenomenally small compared to the proton, its charge is exactly the same as the proton's charge, except it's opposite. So their charges cancel away, but their masses are completely different. Okay? All right? It has a symbol E with a little superscript negative to represent its charge. It's located around the nucleus in orbit in some way, and yes, it weighs very little. The neutron has no charge. We give it an N with a 0 superscript there, and that represents the charge. It's found in the nucleus and also has a mass of 1. Are we okay with all those values? Excellent. All right, so let's now talk about, hold on one second. All right, don't write that slide down. Don't write that slide down. Are you guys so quick? You already got it down? You okay? All right. This is really just a list of 3 things that we're going to do for the rest of the period. Different ways in which we can communicate information about atoms. Number 1, atomic notation, and that's just essentially using symbols and numbers to describe numbers of protons, neutrons, and electrons. Next is Bohr-Rutherford diagrams. You've seen those before. They've got the rings and the dots. And last is Lewis diagrams, and I don't know whether you've encountered Lewis diagrams before. They're a simplified version of Bohr-Rutherford diagrams, which are much easier to use when we start describing what's happening when the atoms bond to each other. So I guess the Lewis diagrams is the new thing for you guys today. All right. So standard atomic notation. I'm going to put some labels on here. So I'm going to write a label here and a label here, and I'm going to write some stuff. So I don't know how much room you want to leave around it. I'm going to do some doodling around there in order to explain what these things are. So the symbol on the left, X, represents any element, element X. There isn't actually an element X on the periodic table. There's an XE, but there is no X. So this represents any element. My example, I'm using Si or silicon, and there are 2 numbers that we put in front of it. The superscript A represents the, I've got my pen here, the atomic mass. It's the atomic mass, or sometimes we call it the mass number, okay? So we're just going to call this the mass number, and my pen isn't working. Let me check here. This is the mass number, all right? And I am going to write something underneath here in a moment, all right? I'm not going to write it yet. Z is the, yep, it's the atomic number. The atomic number. And that bothered me right when I first learned it. Why would you give the letter A to the mass number and the letter Z to the atomic number when atomic number starts with A? I hate that. Drives me crazy. I tried looking up where the Z came from, and I never did find the origin or that first scientist who used Z, so I could curse him in my mind. Oh, why'd you pick Z? But it is throughout physics and chemistry, whenever you need to write about the number of, well, what does the atomic number tell us? We talked about it yesterday. Yep. Yeah, so the atomic number is the number of protons. And we did that yesterday. So whenever you come across a mathematical equation where they're calculating some kind of great thing, and I'll talk more about where this comes from, because Bohr actually did math to figure out the rings. He actually predicted the size of the rings. Anyway, in those equations, when you put the number of protons in, the symbol you use is Z. And Bohr even used those symbols back in 1914. So Z was used even back in 1914. I don't know where it came from. I got to do a little more investigating. Mass number A, that's equal to, we do that yesterday when we just did groups and periods. We didn't do these calculations yet. We're doing this today. Yeah, very good. Number of protons plus the number of neutrons. We can put a plus there and there. Now, there's all kinds of different ways now that we can come up with the neutrons. Let's look at this example here. So if I wanted to go through all the fundamental particles, the number of protons in silicon is, what do we got? Miss Eves? 14. I have to say Miss Eves or I'm going to call you by your sister's name, and that would be wrong. 14. Excellent. The number of neutrons. How many neutrons are in this? Yep. 14. How'd you get that? 28 minus 14. 28 minus 14 equals 14. Now, at this point, different teachers might have taught you different, like, mathematical equations to get this. Because you could do this. You could say here, right, if this plus this equals A, right, then I could rearrange this, and I could bring the protons to the other side, and I could say the number of neutrons is equal to A minus the number of protons. Have you ever seen something like that mathematically? That's good, but I don't think this needs memorizing in this place. Look at the number of protons is the atomic number, so we can rewrite this as the number of neutrons equals A minus Z, right? But you know what? Take the big number and subtract the small number, and you're going to get the number of neutrons every time. No need for a big fancy equation, all right? And if you're confused on which number goes where, the big number goes on the top all the time, and the little number goes on the bottom. So it's really simpler than all of that work. Okay, if we're talking about a neutral atom, how many electrons are going to be in this particular atom? We're talking a neutral atom, Marissa? 14, because it has to be the same as the number of protons. Excellent, good. I like the fact that I'm seeing the beginning of some yawns and maybe a little bit of eye rolls. We've seen this, Mr. Sanders, and that's excellent. I want this to be very much review. Do you have all the information you need, Wilson? Excellent. Let's do some examples. Just write down EG. Just write down EG. And don't write down, calculate the protons, neutrons, and electrons. Don't write that down, because that's what we're going to do. You're just going to do that. So write down these two elements, and underneath them put the number of protons, put the number of neutrons, and put the number of electrons. And did I give you guys the speech of doing practice problems? Did I say to you, I might have said to you yesterday, and if I haven't, I said it to some of my other classes. When we start doing examples, use a pencil, right? So you don't, if you make a mistake, and go ahead of me. Don't wait for me. So if you think you know what you're doing, do this example before I even get to doing the example. Do it with a pencil, do it quickly. If you're not sure what's happening, then you're going to wait. You might want to wait. But if you do it right because you know it, then you're going to gain confidence. You're going to say, hey, I did know how to do this. So do the number of protons, do the number of neutrons, do the number of electrons. Same thing with this one. Number of protons, number of neutrons, number of electrons. Finished? Nice. Can you tell me all three of them here for this one? What do we got? 33, 42, 33. Do we like it? Supporters? Excellent. Thumbs up. Somebody want to do the next one for me? Megan, what do you got? The back. 19, 20, 19. We're doing some simple addition today. Hard stuff, isn't it? All right. We okay? All right. So let's now talk a little bit about Bohr diagrams. I do want you to draw this and just just to recall Bohr-Rutherford diagrams. We used to just call it Bohr diagrams. I like the fact that they included Rutherford's name, because Rutherford is really, I think he's the more significant scientist in this particular discovery. Discovering the neutron was, discovering the nucleus was huge in the study of the atom. Bohr's contribution was exactly how to distribute the electrons in orbit. This is just an iconic representation of the atom. The atom looks nothing like this. Even back when Bohr did his calculations, before they knew about what weird things were going to come, this still was not a good representation of an actual atom. What features of this representation of the atom are incorrect? Does anybody have any ideas? If this was a real atom, how would things look differently? Any ideas? If this was a real atom, how would our picture look differently if we were representing something closer to reality than just spaces to put numbers and dots? Yeah, Marissa, what do you think? It would be phenomenally smaller. You actually probably wouldn't even see it as a pixel on that screen with the size of the orbits there. The nucleus is so small compared to the size of the orbits. Like I said, you wouldn't even see the dot that represents it. All right? There's also a second feature that I don't anticipate anyone will guess, but I'm going to tell it to you. Like I said, Bohr didn't just wake up one day and jump out of bed and say, I got it! They're in rings. What was I thinking? And the first ring is going to have 2, and the second ring is going to have 8, that's not the way, science is actually done. He didn't actually just, oh, I got a great idea. He did all kinds of math. And like I said, in the equation that he used, when he inputted the information needed for the nucleus, the letter was Z. Now, Bohr knew all kinds of physics. He was a physicist. So he knew that a nucleus being positive and an electron being negative would have a force of attraction to each other. All right? And that force of attraction, we call it electrostatic force. You talked about it in grade 9, right? Did you guys do some electrostatics where you took the fifth ball and you charged it with a nice little piece of rabbit's fur and you did that type of thing, right? I have a little bit of rabbit's fur here, right? I don't know what happened to the rabbit itself, but that type of stuff. That's exactly the same forces that govern electrons and around the orbit. When he did the mathematics, he came up with an equation that determined the radius of each of the orbits. He also came up with the equation that determined the number of electrons in the orbits. So the number of electrons in the orbits comes from mathematics. Same with the size of the orbits. It comes from mathematics. And the radius of the orbits has some kind of constant number. Let's just call it K. And that constant number is multiplied by n squared, all right? Where n is the orbit number. So for the first orbit, if n is equal to 1, his radius would have just been K, all right? But for the second orbit, it would be K times 2 squared. What's 2 squared? 4, which means the second orbit is 4K. So it's not twice as far away, it's 4 times as far away. How far is the third orbit going to be? R3 is going to be K, n is 3 squared. How far away is the third orbit? Yep. 9K. It's 9 times farther away from the nucleus. If I were to actually try to draw a representation of that, if this was the nucleus, and that was 1K, then the second one has to be 1, 2, 3, 4. There's the second orbit. And the third one has to be 9. What was that? That was 4, 5, 6, 7, 8, 9. Did I do that right? It should be significantly further. No, that's not bad. That's the first. That's the second. So that's 9. Where's the fourth one going to be? Where's the fourth one going to be? 16. 10, 11, 12, 13, 14, 15, 16. It's out here. Where's the fifth one going to be? 25. It's going to be across the hall. So the orbits grow in size very quickly. The atom gets big really fast. So when you go from here to here, it's not twice as big. It's 4 times as big. And this atom is 9 times as big as the first one. And this atom is 16 times as big. The atoms get huge very quickly. That doesn't do anything for you right here, right now in this course. But in grade 11, we talk about how that size affects the way the atom behaves. And it's very important in the future. So I'm giving you guys a little heads up on that. All right? So this picture, not a great picture, because the atom should be huge. The third one should be way out there. We're not going to draw it like that. You won't have enough space on your paper if we draw it like that. Okay, let's do a couple of one energy level equal to the Bohr number. That's on the same period of the same number of energy levels. Handout Bohr diagram. Hold on 1 second. Example of drawing a Bohr diagram. Draw a Bohr diagram for lithium. Find atomic number. Shortcut. Let's go right to this. Go to example. EG. Just put EG. Wherever I write example, just put EG. All right? And don't draw the Bohr-Rutherford diagram for lithium because we're under the note, Bohr-Rutherford diagram. Just put lithium. And I'm going to do that right here on the board, the smart board. So lithium. I'm going to write here Li. I don't know if we necessarily need to write these rules down. let's just draw it out, see if you need to write them out or not. We know we've got to draw a circle in the middle to represent the nucleus. We now have to find the atomic number. What's the atomic number for lithium? Yep, 3. This number represents how many protons and electrons there are. Find the mass number and subtract the atomic number. This represents the number of neutrons. In lithium, the mass number is approximately 7. So how many neutrons? Yep, Megan up front. 4. So in the circle, we're going to write, and it's hard to write it in there because it doesn't fit very well. And I really don't care how you write it in. What do we got? 3 protons, 4 neutrons. And I think you would have did that last year, right? You would have did all kinds of calculating of neutrons and protons and probably drove you crazy. Now for the orbits. First orbit. How many electrons are there in lithium? Yeah, Marissa? 3. How many go in the first orbit? 2. 1. You may have actually put the 2 on the other side. Did you guys put the 2 on the other side last year? In reality, it pairs up. I like putting them beside each other. Yep.
Last year when we were drawing the rings, you had to do like dashes for them.
Did you?
Yeah.
I just do full circles. Actually, you know what? I'm going to teach you a shortcut in a minute where we're not even going to use rings. This is just to remind you of what you did last year, and now I'm going to show you the way I want you to think this year. So this is good. Don't worry about it. And I'm not worried about dashes versus solid. I do want the dots to be, you know, if I'm doing dots, I need the right number of dots, right? Second orbit. And how many dots go in that one? 1. Oh. And the eraser doesn't work. The eraser doesn't work out. I don't know why I put 2. I'll tell you why I put 2. Because now I'm thinking I might want to change things up for the shortcut. Because when you did this last year, did you put the dots spread out nice and evenly on the surface? No. How did you put them? Put them where? Just dot them on there. Oh, wow. This is an issue. All right.
We did like the right numbers,
Yep.
but we just didn't care about
Yeah. Okay. I'm going to get rid of this one here. Just ignore that one. So for our diagram here, you just put the 1, right? That's lithium. Okay. What I was going to do is I was now going to show you the shortcut. Shortcut. Do not draw the dots. Write the numbers from this point forward. Ignore the. Don't write that down. Don't write that down. Okay. Here's what's going to happen. Do you have the sheet? Do you have the sheet for drawing the Bohr diagrams? Excellent. That's the sheet there. If you don't, you're going to be trying to draw grids, and it's going to be a pain. Now I'm going to ask you to. How do I want to do this? Because I do want you to think about where the dots go. All right, I'm going to ask you to, let's not worry about that shortcut note right now, for now, and I'll come back to it in a minute. Okay, so let's work through the Bohr diagram sheet together then for a moment. I want you to ignore the neutrons. I don't care about the neutrons, because the neutrons don't affect the chemistry. They affect the mass number. That's it. So let's not worry about the neutrons. So let's start in the hydrogen box. I'm going to just write an H here. You're in the hydrogen box. Everybody okay with that? And I'm going to put the circle, and what am I going to put there for the number of protons? 1. Don't even write P in there anymore. Just put +1, because we're really only interested in the charge. Now the shortcut doesn't have you draw the entire circles, but I do want you to draw the circles, and I'll explain why in a moment. So I am going to have you draw the whole circle, and it's going to have 1 electron in there. Now I'm going over to hydrogen. Sorry, to helium. And if you already see the idea, you're going to go +2. Go ahead on that. And you're going to put the circle, and you're going to put 2 dots. But I'm now going to tell you that the electrons like to pair up. They're all negative, so they want to get far away from each other, but there are certain times when they will pair up. There's a complicated reason behind it. It has to do with their spin, and their spin creates a magnetic field, and when they get together, they spin in opposite directions, and those two magnetic fields bring them together like two little magnets sticking together. You don't need to know any of that. But that's what actually happens in an orbit. So electrons will pair up when they're forced to. And in this case, there's only two electrons, so they do pair up. All right? So I want you to draw it like that. Let's now get over to lithium. Lithium is, and you go ahead, +3, put a circle on there. You're now going to draw those like that. And you're going to put in the next one, and I want you to put the dot at 12 o'clock, if it was a clock face. Because this is going to make your life a little easier in the future. Now we're moving over to beryllium. And beryllium is +4, and here we're going to put that there because there's no other place. They've got to pair up. But in the second orbit, there is space for 8, so they don't pair up until they have to. So they don't get into pairs yet. We have one go there, and I like to draw the second one at the 3 o'clock position. You could draw it at the 6 o'clock position. It wouldn't be wrong, but I like to draw it as if we're going around a clock. So now we've jumped across the transition metals, and we're looking at boron, and that's looking like 5 and 2, and now we've got 1, 2, 3, like that. Okay? All right? I'm going to clear the screen here so that I can continue. God, smarten up. Okay. It's supposed to be a smart board, isn't it? All right, clear the screen. Clearing. Where am I at? Carbon? +6, 2 in the middle, and now 1, 2, 3, 4. Our 4 electrons on the outside of carbon are separated as far as they can go. Moving on. Again, go ahead of me if you think you know the idea. What am I doing? Nitrogen, +7, 2 paired up. We've got the 4 singles, and now they have to start pairing up. So once we add the 5th, we now have a pair. All right? And it continues to pair up until we get to the end of the row. When we get to neon, all right, and then that gets us to, and I'm going to just jump ahead to neon. I think we're at +10 at neon. And at neon, everybody is now paired up, and we now have that full outer shell. So you learned in the past that an atom is happy when it gets a full outer shell. But the more truthful answer, see, Abby, you were lied to a little bit last year. It's not just the full outer shell. Atoms are happy when all their electrons are paired up. It's about pairing electrons up that is really more important to atoms than just a full outer shell. Now, it turns out that at the level of chemistry I'm going to teach you, when you pair everything up, everything gets a full outer shell. But as you get to learning more and more chemistry in grade 11 and grade 12 especially, I can make chemicals, I can make compounds out of the transition metals where they just pair up some of their electrons, but the outer shell isn't necessarily full, but they've paired them up as best they can, and it makes them happy. All right? And I put quotes around happy because atoms are neither happy nor sad because they don't have little brains and little emotions, even though we say that. All right? Okay, so I want you now to run across all the way to argon, and then I want you to stop there. Okay? So I'll give you a little hint. Sodium now is going to have 11. I know it's going to be tight, but you've got that full outer shell. Now your second orbit is full too, so you're going to have to put 8 of them around there. And you don't have to count 1, 2, 3, 4 around the clock and 1, 2, 3, 4 again. You can pair them up like that. All right? And then the third one, we're now back to putting that last one. So we've used 10. We've got 11. I'm going to put 1 right there. Sammy, question? Yeah, by all means, go ahead. Just go out the back door there. Don't worry about the hall pass. Just don't get into trouble. Like, don't pull a fire alarm or start a fight. Or go for a smoke. I don't know you people. You might all be smokers. I have no idea. Oh, I recorded all that. That's fine. You can go home tonight. You can listen to me say that again. Don't tell your parents. Okay. So, you think you're okay to run all the way across that road, get to argon? Can you do that? Or do I need to show you all the steps? Can you do it? You can do it. You go ahead and do that. Don't fill in the potassium and the calcium, because I'm going to now show you the shortcut for the last two. But I did need to see you the way it pairs up, because it's very important to know the way they pair up. It's very, let's just say it's very important. It's going to make your next step really easy. Okay, so now you're ready to roll in terms of doing potassium and calcium. Let me show you how we do the shortcut at this point. Once you've made enough Bohr diagrams in your life, I'm hoping you realize there's a pattern to the number of dots that goes around them. Like if you notice nitrogen here, nitrogen has in the outer shell 5 dots, 2 of them are paired up, and 3 of them are alone. And if you take a look at the phosphorus one you just did, and look at its outer shell, you'll notice the same thing. 2 of them are paired up, and 3 of them are alone. That's why they behave chemically the same way, because they have this particular configuration. So I'm hoping we now can figure this out, depending on where we are. But sometimes we don't care about exactly where the electrons are. Sometimes we just care about how many electrons there are. And so in the shortcut method, it looks like this. So I'm going to now do potassium, all right? Again, I start with the nucleus, and you can put this in your chart. So, or you could put shortcut method if you don't have a chart. All right. So, again, we need the number of protons in there, so plus 19. And now, instead of writing all the dots, we do it like this. We use a semicircle that's broken in the middle, and I put a number 2 to represent there's 2 electrons in that orbit. Instead of drawing dots. Much easier. My next one is going to be broken as well. How many are in my second orbit? 8. And this is kind of handy because I don't have to draw all those dots. How many are in the third orbit for potassium? 8, because it's still full. And how many are in the last orbit for potassium? 1. 1. So that tells us, in a quick little way to write it, whether we've got a full orbit or not, because we can look to see if it's 2, 8, 8, or 8, or whatever it is. Do the shortcut method for calcium as well. So do the shortcut method for calcium as well. Seeing the trends? Awesome. It's all about the trends. I'm not going to draw it in, but the shortcut method should be 2882. Ooh, isn't this exciting? With 20 protons in the nucleus. All right, let's just notice some of these trends. What do you notice about the number of orbits for the elements in the same period? What do you notice? So if you run across the period, what do you notice about the number of orbits? Yep. It's the same. What happens to the number of orbits as you go down a group? What do you think? No, look at your orbits as you go down the group, as you go from one down to the next, down to the next. What happens to the number of orbits? Yeah, what do you got there, Connor? Goes up by 1. Increases by 1. You should write that out as a sentence. Don't do what I do. I'm a bad influence on you kids. Use your words. What is the period number the same as? Yep, Megan. The period number is the same as the number of protons. So you're telling me all these elements in the third period have 3 protons? The number of orbits. Good. It's the same as the number of orbits. That's a quick way for you to tell how many orbits we're dealing with. If it's in the 4th period, it should have 4 orbits. What do you notice about the number of electrons in the outermost orbit for elements in the same group? So now we're looking down. Yep, they're the same. That's very important, all right? Very important. It means that we can look at the group number and we can actually tell how many electrons are in the outermost orbit. How does this number compare to the group number? Oh, I just gave it away. It's the same. The number of electrons in the outer shell is the same as the group number, except over here, it's the same as the last digit in the group number. Okay? How does this compare to the group number? It's the same. Group 1 has 1 electron in the outer shell. Group 2 has 2 electrons in the outer shell.
Mr. Sanders?
Yep.
Get your attendance to the office, please.
Yep.
Thank you.
Group 3 has 3 electrons. Notice I said group 3, even though it's 13. I ignore the transition metals because we don't deal with that here. Okay? All right. Now I'm going to quickly talk to you about what a Lewis diagram is. What's going on here? I want this. This. Drawing Lewis diagrams. Don't worry about the attendance in a minute. This is important. Don't tell Mrs. Beatty that I fluffed her off. I'm still recording all this. Why am I doing all this? Goodness. It turns out that in chemistry, the only thing that really, there's 2 things that matter. The number of protons and the number of outer electrons, just the outer ones. Those filled shells, they don't participate in bonding in any way. They're not part of bonding. So a guy by last name Lewis, can't remember his first name, terrible. Anyway, he simplified this idea of diagrams so that all we had to know was what element we're dealing with and how many electrons there are in the outer orbit. And with that simplification, we can make our diagrams much easier than drawing all these circles and things. Notice it says, use dots or X's. I like to use dots primarily. I'll sometimes use X's. I'll let you know when. The symbol has 4 sides. We've already seen that. 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Each side can hold a maximum of 2 electrons each. I just showed you that in the updated Bohr diagram. So you've already essentially seen a Lewis diagram. Now we just got to get rid of all the other fluffy stuff and draw it quickly and efficiently. Fill each side with 1 before you double up. I already introduced you to that too as well. 1, 2, 3, 4. Then we do 5, 6, 7, 8. And we only care about the outer orbit. So a quick way to tell how many dots to put is to look at what group it's in. 4, 5, 6, 7, 8. Just put EG. Just put examples. Oh, goodness gracious. I could, but I'm also looking at the clock. Don't look at me. You keep writing. Pressure is coming. Don't you feel the time ticking by? I can. It's causing me stress. Hurry. All right, look over for friends. All right, look at the neighbors. So, example, e.g., lithium. Black is no good. We put the symbol as the center. We look to see what group it's in. It's in group 1. It has 1 electron. Therefore, I put one dot right there. That's it. That's the Lewis diagram. Let me see. I don't remember the PowerPoint. What other examples does it have? Oh, sorry. That's under Bohr diagrams. Chlorine Bohr diagram. Goodness gracious. Let me just do some examples. I'm working my way across the periodic table. Boron. How many dots am I putting around it? 3. 1, 2, 3. Yep. Aluminum. How many dots would you like to put around that? Yes. 1, 2, 3. It means they have the same number of outer electrons, and that's all that matters about the chemistry. I don't care about what's happening on the inside. What's that? You only do the outer ring because it's only the outer electrons that participate in chemistry. The rest of them stay on the inside. I could do phosphorus. How many dots for phosphorus? 5. Once you get good at it, you don't have to go 1, 2, 3, 4, 5. If you're good at it, you can go 2, 1, 1, 1. Right? I can even now do the ones way down here because they behave the same way. What about bismuth? How many dots would go around bismuth? Yep, Megan? 5. Oh, I just did 5. I know that it's going to be 2, 1, 1, 1. So I'm going to just go. You don't have to make the dots look like pretty dots. When chemists get going and they're in a hurry and I need to draw a bromine, how many dots am I putting around bromine? Putting 7. I do it like this. Done. All right? Supposed to be quick. What if I'm talking about krypton? How many dots am I putting around krypton? Yep, 8. Now I'm going to trick you. Special case. Helium. How many dots am I putting around helium? 2. Even though it's way over there, it's a special case. And I want them together. They've got to be together because they pair up. Because you can only put 2 in the first orbit, so it's got to go that way. All right? We've done enough examples. We're to about 10 minutes left. Your homework is to finish the Lewis diagram sheet. Okay? And that Lewis diagram sheet, I'd like to clear this slide. I'm just going to guide you to the Lewis diagram sheet here. Clear ink and day's work. And many of you have already printed it out. That's awesome. If you haven't, shame on you. You know who you are. Missing out on a good education here. So for this one, it says, do them all the way up to calcium again. Go ahead and do that, all right? And then down here, what trends do you notice about the Lewis diagrams in all the groups? It's the number of dots. That's not a tough thing. But down here is the real practice. Use your periodic table and put the appropriate number of dots around each of the symbols. Okay? Find it on the table. Find what group number it's in. Put your dots around it. Okay? All right? So that's your homework. I do have the answers to this in the homework solution sections on the course content page. Any questions or concerns about Lewis diagrams? Like, once you've done Bohr diagrams for 2 years, Lewis diagrams are like the most awesome thing in the world because you can just slap it down on the page. And really, they're great because they really guide us to be able to do chemistry with great ease. All right, I'm going to stop my recording and we'll send the attendance.